In this video, we're going to talk about corrosion kinetics, part 1. And at the end of this video, we're going to cover the principles of electrochemistry, corrosion rate expression and its calculations, and Faraday's law. Now, one may ask, why do we need to study corrosion kinetics? From our previous video on dynamics, it was established that the dynamics gives us the indication of the tendency of the electrode reaction to occur, whereas the electrode kinetics, which is what we are doing, addresses the rate of such reaction. That is how fast the reaction will take place. And one may ask, what is the importance of restudying corrosion kinetics? And the first one is, it helps us to develop new corrosion resistance materials. Corrosion resistant materials. And also the B, it's help us to improve on corrosion control method. So these are the two main reasons why we need to study corrosion kinetics. Now we have corrosion expressions, that's corrosion rate expressions. In this video, we are going to look at the two modes of expression, which we have the weight loss or per unit area per unit time, whereby it's expressed as the corrosion rate is equal to the material reacted all over the area times time. And with this, we have the corrosion current density, which is represented by I. So the corrosion current density is equal to the current, which is I over A. Therefore, the unit can be expressed as the amps per centimeter squared. Let's note something here, right? For this, we can establish that the corrosion rate, which is CR, corrosion rate, is directly proportional to the corrosion current density. Therefore, when more electrons are released, higher current is also released. And therefore, the corrosion rate increases, because when the corrosion rate is directly proportional to corrosion current density, when there's high in current density, that means that the corrosion rate will also increase. Now let's look at the Faraday's law. In this video, we're going to focus on the first law of Faraday, or Faraday's first law. And with Faraday's first law, an amount of chemical change occurring at any given electrode, as the dissolution, which is anodic reaction, or the position, the cathodic reaction, is proportional to the quantity of electricity passed through the electrolyte. And in this case, we can express that W is directly proportional to Q, which is the charge. And we know that Q is equal to I times T, that's the current times T. And when we do substitution, we could know that W will be with a constant. In this case, let's take the constant to be T times the current. Therefore, W is equal to, now for the Z, which is the electrochemical equivalent, it can be expressed as the atomic weight all over the number of electrons transferred times the Faraday constant. So multiply by IT. When you do all this derivation, you end up getting that the corrosion rate, which is R, is equal to the mass reacted all over the area times what the time, which is equal to the atomic weight times the corrosion current density all over the number of electrons transferred times the Faraday constant. And with this formula, it's mostly for reaction that's undergo without penetration. So it undergo without penetration. And in this case, this formula is used to find the corrosion rate in MGD, which is milligram per decimeter squared per day. That is when we use this formula. Now let's talk about with penetration. So with penetration. So with penetration, the unit, you find it in mm slash y, and MPY, or IPY. We have a lot of units, but we're going to focus on this 3-1. So for this 3-1, when you want to use the corrosion rate formula, the corrosion rate formula is equal to the mass reacted all over density times what? The area times time. Because of penetration, you need to introduce density, which is equal to the atomic weight times the corrosion carrying density all over what? Density times what? Number of electron transfer times what? Faraday constant. Now I'm going to introduce another formula, which in this formula makes it very simple during calculations. You're going to get that a constant, this constant changes when you are dealing with MMY or MPY, times the molar mass times the corrosion carrying density all over the number of electron transferred times density. And as I said, this constant changes when solving with MM/Y or MPY. We're going to do an example and you see that. And now sometimes they can ask us to convert MDD. You solve it in MDD and they say that change it to what? IPY, inch per year. And with that, you're going to find it that for you to change in that case, you're going to multiply the MDD times 0.00144 all over density to change it to what? IPY. Let's take note of this. Now let's take this example. Now the first example is asking us to still corrode in an aqueous solution. The corrosion carrying density is measured as 0.1 amps per centimeter squared. Calculate the weight of loss per unit area in units of MDD. And they gave us the atomic weight of iron to be 55.85 gram per mole. So what you need to do now, first you need to write a reaction to know the number of electrons transferred. So iron, and undergoing this, we have 2 plus 2 electrons. So we now know the number of electron transferred. It's very important. Now for us to find it in MDD, corrosion rate is equal to the mass reacted all over what? The time times the area is equal to what? The atomic weight times the corrosion carrying density all over the number of electron transferred times what? The Faraday constant. From here, let me brief you on something. Now, the MDD means that milligram per decimeter squared per day. But when you solve it with this, what you're going to get is gram per centimeter squared per what? Second. So therefore, what you need to do is that you need to change the gram into what? Milligram. Change the what? Centimeter squared into what? Decimeter squared. And then change the second to what? A. And to do that, what you need to do is that for you to change the gram to milligram, you're going to multiply the gram by what? 10 exponent 3. For you to change this to this, you're going to multiply by what? 10 exponent 2. And this you're going to multiply by what? 24 times 3,600 to convert into this. Note that the reason why it is positive is because it's per, right? It's 1 over that. That's why it's positive. You should understand that. So let's do this example. So now let's do the substitution. So CR is equal to the molar mass, the atomic weight was what? 55.85 times the corrosion carrying density was what? 0.1 all over. Let's do the let me take my calculator. Let's all over the number of electron transferred is 2 times the Faraday's constant is 96500. And what are you getting? I'm taking my calculator. 55.85 times 0.1 all over 2 times 96500. And what you're going to get is that's what you're going to get is 2.8937 times 10 exponent negative 5. This you need to be gram per centimeter squared per second. So for you to convert this into milligram per decimeter squared per day, you are going to multiply it by this factor, 10 exponent 3, 10 exponent 2, multiply by 24 times 3,600. So what you do now is that, what I usually do is that you come here, CR is equal to 2.8937 times 10 exponent negative 5 times 10 exponent 3 times 10 exponent 2 times 24 times 3600. And in that answer, we are going to get this. So let's do that. Times 10 exponent 3 times 10 exponent 2 times 24 times 3600. And what I'm going to get is 250,022.7979 MB. Very simple as that. Let's take note. It's very simple. Let's take example 2. So with example 2, iron is corroding at a current density of 1.69 times 10 exponent 4 ounce per centimeter squared. What is the corrosion rate in MDD and MPY? So the atomic weight of iron is 55.85 gram per mole, and they gave us the density to be what? 7.86 gram per centimeter cube. This is because of what? MPY, because that deals with what? Penetration. So let's solve A. With MDD, we establish that first you need to find your unit in gram per centimeter squared per second. So in that case, when doing that, what you do is that corrosion rate is equal to the mass reacted all over the area times time, which is equal to the atomic weight times the corrosion carrying density all over the number of electron transferred times Faraday constant, right? So in that case, let's do some substitution. So when we are doing the substitution, corrosion rate will be equal to what? The atomic mass was given to us at 55.85 times the corrosion carrying density is what? 1.69 times 10 exponent negative 4 all over number of electron transferred. You've done that balance 1, so it will be 2 times the Faraday constant is 96500. So when we do that, what are you getting? Let's use our calculator. Let's go back to our calculator. 55.85 times 1.69 times 10 exponent negative 4 all over 2 times 96500. And what was your answer? My answer gave me 4.89 times 10 exponent negative 8 gram per centimeter squared per second. So for us to change this to MDD, we first multiply by 10 exponent 3, multiply by 10 exponent 2, multiply by 24 times 3600. So let's do that. CR is equal to 4.89 times 10 exponent negative 8 times 10 exponent 3 times 10 exponent 2 times 24 times 3600. What are we getting? So times 10 exponent 3 times 10 exponent 2 times 24 times 3600. Your answer you're going to get is CR is equal to 122.53 MDD. That's very simple as that. Now let's look at the MPYs. Let's pay attention here. MPY. For MPY, corrosion rate, CR will be equal to what? The mass reacted all over the density times the area times time is equal to the atomic mass times the corrosion carrying density all over the number of electron transferred times density times Faraday constant. Now I gave you another formula which states that there's a constant multiplying the molar mass times corrosion carrying density all over the number of electron transferred times density. Now with this, I'm going to show you how you can use this. Very simple. Now I told you that this C is a constant, right? For you to use this formula, there are conditions for you to establish. First, you must make sure that the I is in microamps per centimeter squared. And secondly, when it is in microamps per centimeter squared, the C, which is a constant, becomes 0.129. Very simple. So how do you convert any given corrosion carrying density into microamps per centimeter squared? Let's note that 1 microamps is equal to 10 exponent 6 amps. So what you do now is that you just multiply 10 exponent 6 to the corrosion current density. In this case, the question they gave us was the corrosion current density was what? 1.69 times 10 exponent what? Negative 4 amps per centimeter what? Squared. So in this case, you are going to multiply this by what? 1.69 times 10 exponent negative 4 times 10 exponent 6 to change it to microamps, and then I'm going to get 169 microamps per centimeter squared. So always you change it to microamps per centimeter squared, and then you just do substitution. you come back, your CR will be equal to what? 0.129 multiplying the molar mass was 55.85 times 169, which is the corrosion current density in microamps, all over the number of electron transferred is 2 times density 7.86. Let me confirm from the density. Yeah, 7.86. So you take your calculator, 0.129 brackets open, rows 55.85 times 169 all over 2 times 7.86. And when you close the bracket, what you're going to get is that you're going to get your corrosion rate in MPY to be 77.455 MPY. Very simple. Let's do this question. Now let's do another one. They said a sample of zinc corrodes uniformly with a corrosion current density of 4.2 microamps per centimeter squared in an aqueous solution. What is the corrosion rate in mg, that's milligram per decimeter squared per day? And what is the corrosion rate in mmY, that's mm/y, which is year? Now let's try this. You can pause the video and do it. I'm purposely concerned about the mm/y, but you can do the mg, that's mdd. You should do that and let me see it at the comment section. So in this, let's solve A. For mdd, very simple as that. You know that the corrosion rate is equal to what? The mass reacted all over what? The area times time, which is equal to the atomic weight times corrosion current density all over the number of electron transferred times the Faraday constant. And we know that zinc corroding, zinc 2 plus or 2 electrons. So the number of electron transferred is what? 2. So let's do substitution. So Cr is equal to, we have the atomic weight of zinc. So we have the atomic weight of zinc to be 65.38, then times the corrosion current density is 4.2 times 10 to the negative 6. You need to change it to the amps per centimeter squared all over. We have the number of electron transferred is 2 times the Faraday's constant 96500, and at the end you are going to get your answer, and that answer you are going to multiply it by 10, multiply it by 10 exponent 3, 10 exponent 2 by 24 by 3600, and at the end your answer in MDD will give you 12.29 MDD. Should we solve it? Okay, I hope you've gotten it, but let's solve it. So with this, when you take a calculator, you're going to get 65.38 times 4.2 times 10 exponent negative 6 all over 2 times negative 6 all over 2 times 96500, and you are going to get, what you're going to get is that you're going to get 1.422 times 10 exponent negative 9 gram per centimeter squared per second. So to change it to milligram per decimeter squared per day, you multiply by 10 exponent 3, 10 exponent 2, 24 by 3600. So let's do that. So you are going to get 1.422 times 10 exponent 3 times 10 exponent 2 times 24 times 3600, and at the end what you're going to get is 12.29 MDD. Now let's look at B. For question number B, we are supposed to convert it to mm/y. I love it. For B, we are supposed to find it in mm/y. So the corrosion rate is equal to the mass reacted all over the area times time is equal to the atomic weight times, now this is penetration, so times density, don't forget that, times the corrosion current density all over the density times the number of electron transferred times Faraday constant. And this can be expressed as, we using the formula that I show you, that we have a constant which is C, which changes individually. When you are dealing with mm/y is different, and when you are dealing with MPY is different. So times the molecular weight times the corrosion current density all over the density times the number of electron transferred. Now I told you that for us to use this formula, you need to know that the I is in what? Microamps. In this case, our I is in microamps already per centimeter squared, which is our I is equal to 4.2 microamps per centimeter squared. So we are lucky. Therefore, if it's like that, then our C here becomes 0.00327. note that for mm/y. So you just do substitution, whereby corrosion rate is equal to 0.00327 times the molar mass, which was given as 63.838, yes, 65.38, then multiply by the corrosion current density, which is 4.2, all over the density given, which is 7.14, times the number of electron transferred is 2. So you take a calculator, 0.00327 times bracket open 65.38 times 4.2 all over 7.14 times what? 2. Then you close it. So the answer in MPY is going to give you corrosion is MPY going to get 0.0628 MPY. So we are moving on to the equivalent weight and density of alloys. So with equivalent weight of density of alloys, we have the element, we have the weight, we have the number of electron transferred, we have the density, we have the atomic weight. And this question is asking to find the equivalence between the corrosion density of 1 microamps per centimeter squared and the corrosion rate in MPY. Luckily for us, let me teach you something. We are going to use the same formula, right? Since that I is given us in microamps, 1 microamps per centimeter squared, and we are supposed to find this in MPY. We are going to use this formula. You know that corrosion rate is equal to what? The C, which is a constant, times molar mass times corrosion current density in microamps per centimeter squared, all over the number of electron transferred times the density. So since the summation, then you're going to do that corrosion rate is equal to the C times the summation of the molecular weight times the corrosion current density all over the number of electron transferred times the density times the weight. So we are finding the summation. So what do? Since we are doing it in MPY, what will be the constant? Because I is always in microamps per centimeter squared. Therefore, C becomes 0.129. So therefore, we have that our corrosion rate is equal to 0.129, a big bracket, and we'll sum everything up, right? So that will be 52.01 times 1 all over the number of electron transferred is 1 times the density 7.1, then plus, let's go to the second one. We have 58.68 times 1 all over the number of electron transferred is 2 times the density 8.9. You do this for all the elements. This is 1, 2, 3. And when you do all, please confirm it on the comment section. You're going to get CR is equal to 0.129 multiplying the total summation. You're going to get is 4.3514. And when you take a calculator and do that, you're going to get that 0.561 MPY. Very simple. It's the same applies to the mm/y when they're given to you in equivalent form. What you do now is that you change the I given to you in microamps, and therefore in mm/y the C becomes what? 0.00327.